Hi everyone, myself Dr. K. from the Department of Civil Engineering. It is my great pleasure to present this which focuses on a fundamentally important tools in the analysis of structure subjected to moving load, the influence line diagram. This concept is not merely a theoretical construct but a practical necessity to ensure the safety and efficiency of some of the most critical infrastructures. So thank you for your attendance. To ensure a comprehensive and structured discussion, we will navigate through the following key areas. We will begin with a clear introduction to the concept of influence line, establishing its definition and purposes. We will then delve into the need and importance of ILD, explaining why these are indispensable in structural engineering. This will be followed by the examination of fundamental characteristics that defines these diagrams. We will then focus on the concepts of ILD for shear force, breaking down its construction and interpretations. Yeah, practical examples will be provided to illustrate the process for a specific sections. We will learn how to determine maximum efforts with these diagrams. The powerful Muller's brushless principle for indeterminate structures will be introduced. Um, and will be explorer practical application across various engineering domains. Finally, we will conclude with the balanced assessment of the advantages and limitations of this method, leading to a summary. So let us begin by defining our core subject. Influence lines or graphical representation that tracks the variation of a specific structural response, be it a support reaction, a shear force, a bending moment, or even a stress at a single specific point in a structure as a standardized unit load traverse across it. Think of it as a diagnostic tool that reveals the sensitivity of a particular point in a structure to the movement of the load. Why it is so essential? Because once this diagram is constructed, it instantly tells us the position a load must occupy to produce the absolute maximum effect at the point. This is not just academic, it is a bedrock of for designing structure like bridges and cranes where loads are perpetually in motion. To be more formal, an influence diagram is a plot where the x-axis represents the path of moving unit load from the start to the end of the structure. The y-axis represents the magnitude of the structure response we are interested in, whether its reactions at support A, the shear at the section C, or the moment at point B. A key characteristics which will be explored later is that of statically determinate structure, which are more primary focuses today. These diagrams are composed of a straight line segment, making them relatively straightforward to construct. The utility of influence lines is profound and multifaceted. They provide a rapid and systematic method for determining the value of reaction, shear force, or moment at a given section under any conceivable systems of moving load. A single point load, a uniformly distributed load, or a various of concentrated axial load from a truck or a train. They are the unlimited tool for identifying the critical load position that governs the design of your member. This eliminates that need to tedious trial and error calculation. Their importance is so widely recognized that they are underlying basics of live load specifications in major bridge design codes worldwide, such as in Indian Road Congress (IRC) and the American Association of State Highway and Transportation Official (ASTO) codes. Now let us focus on the constructing of an ILD for shear force. Imagine we want to know the shear force at the specific section, say section C of a simply supported beam as a unit load moves from left to right. The shear force at C changes. The ILD is constructed by calculating the shear force at C for every possible position of the unit load. The resulting diagram will typically shows the discontinuity of the section C itself. When the load is at the left of C, the shear force is positive. The moment the load passes to the right of the C, the shear force becomes negative. The diagram provides the complete visual history of the shear force at C for the moving load. Similarly, for a bending moment, the ILD for the section shows how the moment at the sections varies the load position. Unlikely the shear force diagram, The bending moment ILD is the continuous functions, typically triangular in shape for the simple support beam. The peak and the triangular occurs precisely when the unit load is directly above the section of the interest. The ordinates at the point gives the maximum bending moment with the unit load can cause at the section. The value of any other point can be found using the simple geometry, which is powerful features of the ILD. Here you can see the maximum bending moment at the midpoint. So the formula is AB by L. Similarly, for shear force, here it is B by L and here it is the A by L. So some of the assumptions in ILD, like any powerful tool, the construction of ILD rests on the set of fundamental assumptions that defines its scope and the limitations. Linear elastic behavior, the structure most obeys Hooke's law, which means the stress is directly proportional to the strain. The principle of superposition must be valid, meaning the effect of multiple loads in the sum of their individual efforts. The unit load concept, we analyze the structure for a single dimensionless unit load. The result of real loads are to be obtained by simply by scaling the ordinates of the ILD by the magnitude of the actual loads. Statically determined systems, the straightforward method we discuss first apply to determined structures where the ILD are linear. We assume support are perfect hinges or frictionless rollers freely rolls and fixed supports are perfectly rigid. We deliberately ignores that influence of support settlement, temperature changes and dynamic impact. This analysis is for static loads only. Understanding these assumptions naturally leads us to the limitation of the method. For indeterminate structure, for statically indeterminate structures like continuous beams, the IL influence line diagrams are not straight line but complex curves. Their construction requires more advanced techniques such as the Muller's principles. So this method collapses if the material behavior becomes non-linear or plastic, as the principle of superposition fails. The result can misleading if support settlement or deform, which is the common relative. An influence diagram is drawn for one specific function at one specific location. A complete analysis requires a family of these diagrams. The analysis does not account for the dynamic amplification effort of moving loads. Some of the advantages of ILD, despite these limitations, the advantages are compelling, the ensuring and endorsing the relevance. It is dramatically faster than repeatedly analyzing the structure for different load position. It provides a crystal clear visual identification for the worst case load placement. The same ILD can be used for analysis the effort of a single point load UDL by calculating the area of under the UDL. If the foundational tools used for generate the loading rules found in the bridge design code, making it directly applicable for the professional practices. Some of the disadvantages, the primary drawbacks of restriction is linear elastic determined structures under static load. Its accuracy is entirely dependent on the precision which with the diagram is drawn and the area is calculated. As mentioned, it requires multiple diagram for the full analysis and cannot capture real world complexity like support settlement and dynamic effect. Some of the practical applications, bridge engineering for determining the maximum bending moment and the shear force in the girders due to the standard IRC. This is primary application. Railway bridges also it is used for analyzing the effect of multiple wheel load of the train. Crane girders in industrial buildings for designing the girders that carries moving trolleys, ensuring they can be safely withstand the moving load and its effort of the supports. Loading rate for assessing the safe load carrying capacity of existing bridges for determining the actual effect of the model vehicle weightage. Um, in summary, the influence line diagram is a elegant, powerful, and essential tool in the structural engineering toolkit. It transforms the complex problem of analyzing the moving load into the manageable graphical exercise, providing direct insights into the most critical loading conditions. While it has its limitation, its role in the design and the assessment of transportation infrastructures is irreplaceable. So thank you for your attention and thank you.